This lecture will describe the types of problems that we're interested in and we'll solve. We'll also discuss in some detail the problem-solving procedure and then apply it to 3 single unit operation problems. The types of problems we're going to encounter initially fall into these 3 categories. The first is a single unit operation. Then we'll move on to having multiple unit operations, and then discuss operations that have recycle and bypass. We'll be applying the general balance equation in order to solve problems. As we've discussed previously, this balance equation is of the form that accumulation A is equal to input I minus output O plus generation G minus consumption C. We're going to apply this balance to the total mass in a system that's been defined by a control volume, and also to the mass of individual chemical species. Now note that if we don't have chemical reactions, G and C, the generation consumption terms, are 0. And initially, we're going to be looking at problems that are only steady state. So accumulation is going to be, the accumulation term A will be equal to 0. So if we have no reactions in addition to having a steady state process, then we'll be able to say is that 0 is equal to I minus O, or I is equal to O, or just simply N is equal to out. The full problem-solving procedure is outlined here. I'll just briefly go through it. The very first thing is to read the problem statement carefully. This is very important, and most likely you'll read it and start in with the remaining steps and have to come back and read it again. This is a very, very common thing, is that you'll think you have read it enough that you can go through and solve the problem completely, but you often will find you have to go back. The next step is to draw the process flowchart and label the streams to the best of your ability. Step 2 will require often that you convert information given to you to a common set of units. We'll be converting it either to mass or mole units or to a mass flow rate and mole flow rate unit. This next step 4 is real important. If no flows or amounts are specified, you can choose a basis. You're free to choose any one of the streams and to set a value for a total mass or a total flow rate. So for example, one of the streams, if it's involving mass flow, you could say one of the streams has a flow rate of 100 grams per second. Or you could say it has 1 kilogram per hour. Or you could say that it's 1 mole or 1 kilogram. It's totally arbitrary, and it doesn't matter. The results won't depend upon what you choose for your basis. For those variables that you don't know, and for which you haven't assigned a basis, we'll have to assign variable names to them for unknown flows and compositions. And these first 5 steps are things that we've done in the previous lecture. The new things we'll be covering in today's lecture are, first, how do we perform a degree of freedom analysis? This will tell us if the problem is solvable or not. Next, then, we're going to draw a control volume around the process. And within this control volume, we're going to write our mass balances, or for that control volume, we're going to write our mass balances, both an overall balance and species balances. And once we have those written, we're going to try to find one of them that we can solve for one of the unknowns. Or if we're unable to find one equation for which we can solve for one of the unknowns, we may have to solve 2 equations and 2 unknowns simultaneously. And finally, when we're done solving for all unknowns, there may be additional quantities that we've been asked to calculate. In the previous lecture, we talked about labeling the 3 streams associated with this problem statement. The 3 streams were defined by the text in blue here. The first is that 1,000 kilograms per hour of a mixture containing equal parts by mass methanol, which we'll denote by the letter M, and water, which we'll denote by the letter W, is distilled. This stream is labeled right here. Above the arrow, as we did in the previous lecture, we put the amount or flow rate. Here it's 1,000 kilograms per hour. And then below the arrow, we put our composition information. Since it's equal parts by mass methanol and water, the mass fraction of methanol is 0.5 and the mass fraction of water is 0.5. The stream is sent to a distillation column, and the distillation column produces 2 streams, a top and a bottom stream. The flow rate of the bottom stream is measured and found to be 673 kilograms per hour. That information is shown here in this labeled stream. The amount above is 673 kilograms per hour, and below we have composition information. We don't know either of the compositions, so we'll assign a variable x sub 1 for the composition of the methanol. And since we know the mole fraction sum to 1, the mole fraction of water is just 1 minus x1. The last stream is the overhead or top stream. It's analyzed and found to contain 96% methanol. That information is represented in this labeled stream here. We're not told the flow rate, so we use a variable name, m dot, to represent it. And the unit's going to be kilograms per hour. They'll have to be the same as the units for the flow rates of the other two streams. The mass fraction of methanol, we're told in the problem statement, is 96. The mass percent of methanol is 96%, so the mass fraction is 0.96. To convert a percent, such as 96%, to a fraction, you divide by 100. So 96 divided by 100 is 0.96. Since the two mass fractions must sum to 1, the mass fraction of water is just going to be 1 minus 0.96, which is 0.04. So the first 5 steps are complete here. We read the problem carefully. Here, the streams are combined with a process flow diagram. All we have is one square here, one unit operation, which represents the distillation column, this blue square. So we combine the flow chart and the stream information together. Everything's been converted to a common basis. In this case, we're using as our basis, for a unit basis, that we're using kilograms per hour. It's a flow rate, and we're using mass fractions. For this particular problem, we do have a known flow rate. We actually have 2 known flow rates, so we're not going to have to choose. We won't be given the option of choosing a basis for the calculation. And finally, we did assign variables to the unknown flows and compositions. In this case, we have 2 variables that we introduced. One is m dot for the flow rate of the top stream. The other is x sub 1 for the composition of methanol in the bottom. Let's move on to those next steps in problem solving. The next step is to perform a degree of freedom analysis. And if we determine the problem is not solvable, we're done. We can't solve it. To perform a degree of freedom analysis and determine if the problem is solvable, what we need to do is, first of all, count the number of unknowns. Because the problem is solvable if the number of unknowns equals the number of independent mass balance equations. To determine this quantity, to determine the number of independent mass balance equations, all we have to do is count the number of components. The number of independent mass balance equations for a non-reactive system is just equal to the number of components. So let's do this here. Let's look at what this implies here for this problem. In terms of unknowns, we can just list them. M dot and x1, we have 2. In terms of the equations, number of equations, it's going to be equal to the number of components. We have 2 components. We have methanol, M, and we have water, W. We have 2. Since the number of unknowns is equal to the number of equations, it's solvable. The next step is to draw a control volume. Next 2 steps are to draw a control volume and then write mass balances for that control volume. We're going to write the overall balance for that control volume and a balance for each of the species. Then once we have those written, we're going to try to solve for one of the variables at a time. And if we can, our life is easy. If not, then we'll have to use more sophisticated, more complicated algebra in order to obtain a solution. We'll have to end up solving multiple equations and multiple unknowns. Now for this process, which is steady state, so the accumulation term is 0 and there's no reactions, G is equal to C equals 0, our balance equations are all going to be of the form N is equal to out. So here's our process. This red box defines the control volume around which we're going to, which we'll use to define our closed system, and we're going to look for inputs and outputs across that control volume. So first of all, let's look for the inputs. We're going to put flows into that control volume on the left-hand side of the equals, and we'll put flows out of the control volume on the right-hand side. So if we start here with this one input stream, we have this one input stream. The total amount that's coming in this stream is above the line. It's 1,000. So we'll put that over here on the left hand side of the equals for our overall balance. Let's go around and look at what other streams we encounter as we go around the control volume. As we go around over here, the top stream is coming out. Its flow rate is m dot. We don't know it. It's a variable. So in our overall balance over here, on the right-hand side, we'll put m dot. That's one of the flows out. We keep on going around our control volume. The next flow out is the bottom stream here. Its total flow rate is 673 kilograms per hour. We'll put that also on the right-hand side and add it to the flow rate of the top stream. If we keep on going around our control volume, we come back to where we started, to the input. We've now written the overall mass balance completely. We have in algebra here shown that what the flow rate coming in, which is 1,000, is equal to the flow rate coming out, which is the flow rate of the top stream, m dot, plus the flow rate of the bottom stream, 673. This one equation we can actually solve for m dot. We're going to do that in a moment. Now let's look at the balances for each of the components. We'll start off with a balance for the methanol. And we're going to repeat this process. We're going to go around our control volume and determine the methanol flow rates in, put them all on the left-hand side of the equals and sum them, and we'll look for the methanol flow rates out. We'll put them on the right-hand side of the equation and sum them. Let's start just like we did before with this one stream that's coming in. The total flow rate is 1,000 kilograms per hour, and we know that half of that is methanol because the mass fraction is methanol. So the total amount of methanol coming in is going to be 1,000 times a half. If we look over here, we put 1,000 times a half as an input on the left-hand side of the equal sign in our methanol balance. As we work our way around the control volume, we have an output stream here, the top product. The amount of methanol in this stream is going to be the total flow rate, m dot, a variable, times the fraction of that, which is methanol, the mass fraction, and that's 0.96. We come back over here and look at our methanol balance. We see on the right-hand side of the equals, as one of the outputs, m dot times 0.96. This is the amount of methanol that flows out in the top stream. And we're going to add to it the additional output that we have. We keep on going around a control volume. The bottom product, its total flow rate is 673, and the amount of methanol in that stream is represented by the variable x1. So we'll add the product of x1 and 673. We'll add that to the other output of methanol to complete our balance. So the methanol balance is written here, is that what comes in, the flow rate times the composition is going to be equal to what comes out, the flow rate times the composition for each of the streams coming out. This is the methanol balance. Next, we're going to look at the water balance and repeat the process again. We'll come over here. We have one stream. We'll start with this stream coming in. Its flow rate is 1,000 kilograms per hour. And we'll look below the arrow to find what fraction of that is water, and it's a half. We'll take the product of the fraction times the total. We'll put this over here on the left-hand side of the water balance as an input stream. As we work our way around the control volume, the first output stream that we encounter is the top product. Its flow rate is m dot. We look below the arrow to find the composition of that, which is water. What fraction of that's water? It's 0.04. So we'll add over here m dot times 0.04 on the output side of our balance equation. We keep on going around the control volume. We have one more output, which is the bottom product here. Its flow rate is 673, and the fraction of that stream, which is water, is 1 minus x1. Come over here to our balance equation. We add that to the product side, the output side of the balance equation. So we add in 673 times 1 minus x1. So now we've written the overall balance equation and a balance equation for each of the components for this control volume. We've written three equations, an overall balance and one balance for each component. There's two components, so we have three total. Only two of these are independent. Let's review what it means for a set of equations to be independent. To be independent, you should not be able to derive any one of the equations from the others. Now, the overall balance is always equal to the sum of the component balances. So for instance here, if we take the methanol balance and add to it the water balance, you'll find you get the overall balance. Let's do this term by term. On the left-hand side, input, we have 1,000 times a half. That's how much methanol comes in. We add to it the amount of water, which is 1,000 times a half. The sum of those two is 1,000. On the right-hand side of the equals, we'll look at each of the output streams. The top product, its flow rate is m dot, and it's the fraction of that, which is methanol, is 0.96. That's the methanol flow coming out. The flow of water coming out is m dot times 0.04. If I add the flow coming out of, in this stream, of water to the flow of methanol coming out, we have m dot times 0.96 plus m dot times 0.04. 0.96 plus 0.04 is 1, so we just end up with m dot. And then if we look at the other stream, we have 673 times x1, that's the flow rate of methanol coming out. In the water balance, we have 673 times 1 minus x1, that's the flow rate of water coming out in the bottom. We add those two together, we get 673. That's because the 673 times x1 will cancel the minus 673 times x1, which we get when we distribute the 673 across the parentheses here. So this is just an example showing that the overall balance can be obtained by simply adding the component balances. When we wrote it, we didn't do it that way originally. What we did is we went around the control volume and identified each of the inputs and outputs. But if you wanted, you could write each of the component balances and add them together to get the overall as well. So the number of components in the problem is equal to n. We can write n component balances and an overall balance. So the total number of balances that we can write is n plus 1. However, only n of those n plus 1 balances are independent, because as we've just seen, the overall balance is equal to the sum of the component balances. So why do we write one extra equation? Well, when solving problems, it may be easier to use the overall balance instead of one of the component balances. And we're going to see an example of that. So these are the three balances we've written for this example problem: the overall mass balance, the methanol, and the water mass balances. Now we can pick any two of these equations to solve for the two unknowns, m dot and x1. Only the overall balance allows us to solve for one of those two at a time. The component balances, if we look at those, both of these balances involve two unknowns. The methanol balance has m dot in it and x1. The water balance has m dot as well as x1. We can't solve for one of these unknowns from one of these equations. We could solve the two equations simultaneously for these two unknowns. Well, that's a little bit more work than just taking the overall balance and solving it directly for m dot, because we can do that. And so if we write down the overall balance, 1,000 is equal to m dot plus 673, we can rearrange this to show that m dot is just going to be 1,000 minus 673, which is 327. And we know the units of m dot are kilograms per hour. Now, since we know m dot, we can solve the m balance up here for x1. So let's write down the balance for methanol. We have 1,000 times a half is equal to m dot times 0.96 plus 673 times x1. But now we know m dot is 327. So we can solve for x1 by taking 1,000 times a half and subtracting from it m dot, which is 327, times 0.96. If we do that, we get 186, and we know that's going to be equal to 673 times x1. If we simply divide by 673, we can show that x1 is equal to 0.276. Now we've solved the problem. We determined m dot is 327 and x1 is 0.276. That's the mass fraction of methanol in the bottom stream. But we can check our results by plugging our values for m dot and x1 back into the water balance and see if we do get the same amount coming in as coming out. If we plug these numbers in for m dot into our water balance, on the left-hand side we have 1,000 times a half, which is 500. On the right-hand side, we're going to take m dot times 0.00 times 0.04, 327 times 0.04, and add to it 673 times 1 minus x1. We'll add to it 673 times 1 minus 0.276, and we get the same number, 500. So we've just showed that the flow of water in, the left-hand side of the equation, is equal to the flow of water out, and this provides an independent check of our calculations, and I would say our numbers are correct. Let's look at a second example. This is a problem involving 2 inputs and 2 outputs, and it's being applied to a process called liquid extraction. In this particular case, one of the feeds, the 400 gram per minute feed here to the left, is a mixture of A, which is acetic acid, and B is water. And we like to be able to do is to pull out the acetic acid, to remove the acetic acid from the water and to concentrate it. And we can do that by, in this vessel here, mixing the stream, this mixture of acetic acid and water, with an extractant, an organic compound that will selectively remove the acetic acid from the water. And in this case, what we're adding in, we're mixing in, is an alcohol, an organic alcohol, 1-hexanol. If we mix these two together in here and then allow the mixture to phase separate, we can recover a liquid stream that has less acetic acid in it, and an organic stream which has the acetic acid that we removed from the water. And so that's what's shown here. So in this particular problem, a lot of the diagrams have already been labeled for us. We have 400 grams per minute of our acetic acid and water mixture being fed to our liquid extraction device. The mass fraction of acetic acid is 0.115, and the balance is water. We're feeding pure hexanol into the liquid extractor, liquid extraction unit. What comes out of it is a liquid stream, which we don't know the flow rate of, but we do know the composition of it. It has 0.005 mass fraction of acetic acid, and the balance is water. And we don't know the flow rate of the hexanol stream that has the acetic acid in it. We do know the composition of this hexanol stream as it exits, that it has the mass fraction of acetic acid is 0.096, and the balance is the hexanol. So what we're going to do is try to solve for these unknown flows in this particular process. We do know all the compositions. So let's go back to our problem-solving procedure and review the steps. Steps 1 through 5 have been done for us. I actually described the problem to you. The process flow chart and streams were all labeled, were provided and labeled for us. Everything was converted to a common unit. In this case, it was a mass flow rate unit. We weren't able to choose a basis because we do have at least one specified flow rate. And variables were assigned to all the unknown flows and compositions. Next, let's perform a degree of freedom analysis and determine if we can actually solve it. To determine if the problem is solvable, we have to determine the number of independent material balances and see if it's equal to a number of unknowns. The number of balances is equal to the number of components, as we discussed previously. In this particular example, if we look at the streams and work our way around the process, we see that there are 3 components, A, B, and C. Acetic acid is A, water is B, hexanol is C. So the number of independent balances that we can write is equal to 3. If this is equal to the number of unknowns, the problem is solvable. Well, the number of unknowns here is equal to 3 as well. We have 3 unknowns, m dot C. M dot C is the flow rate of hexanol coming in. If we work our way around, m dot R is the unknown flow rate of the water that leaves the process after having the acetic acid removed. And then m dot E is the flow rate of the hexanol leaving the process that has the acetic acid in it. Since the number of balances is equal to the number of unknowns, the problem is solvable. For this process, which is steady state, it has no chemical reactions, the overall balance, mass balance, and the individual species mass balances reduce to the form what comes in must be equal to what comes out. We've talked about this previously. And to guide ourselves in the process of developing and writing these mass balances, the control volume that we're going to use is shown here by this red oval. What we're going to do is go around this and determine either the total amount that comes in or the amount of each of the chemical species and set that equal to the amount that's coming out. The results are shown here. The overall balance is given first, and then the balance for component A, the acetic acid, the balance for B, which is for water, and then finally the balance for C, which is the hexanol, the extractant. Let's see how we got these four equations. First off, let's start with the overall balance. Once again, remind you on the left-hand side, the equals will be the amounts that come in, and on the right will be the amounts that come out. And we'll look at this control volume. We'll start right here to the left. There's one arrow that crosses this that comes into it. This is the feed that we have to the process, the mixture of water and acetic acid. Its total flow rate is 400 grams per minute. That's an input, so we'll put that on the left-hand side of the overall balance. As we work our way around the control volume, we find that there's another stream coming in. That's our hexanol. Its unknown flow rate is represented by the symbol m.c. So add the m.c to the 400 to give what's coming in to our process and to our control volume. As we work around the control volume, we find there's the first stream coming out is the water stream that has had the acetic acid removed. Its total flow rate is m.r. We'll put that on the right-hand side of the equals as an amount coming out. If we keep on going around a control volume, we find there's one more stream coming out, which is our hexanol that has extracted the acetic acid into it. Its flow rate is represented by the variable m.b, and that's added to the variable m.r to get the total amount coming out. And we're going to repeat this process of going around a control volume, determining what comes in and what comes out for each of the three components. So let's start with acetic acid. Let's start where we started before with the overall balance. The water feed here that has the acetic acid flows in with a flow rate of 400, and the fraction of it, which is acetic acid, is 0.115. So in our balance equation over here, we'll take the total amount, total flow in, and multiply by the fraction, which is acetic acid. If we work around the control volume, the next stream we encounter is this input. The mass fraction of acetic acid here is 0. So it'll add nothing to the balance for A. We keep on going around. The next stream that we encounter is the water coming out. It has A in it, the acetic acid, and the amount of A that comes out is going to be the fraction, 0.005 times the flow rate. And that's on the right-hand side of the equals over here as an output. And then we'll add to it the amount that comes out of the other stream, the hexanol extractant, which will be the amount of the fraction of acetic acid, 0.096 times the flow rate of the hexanol, m.b. So we've completed the balance for the acetic acid component A. We'll repeat that for component B, working our way around. Same thing, we'll take the total amount above and multiply by the fraction below to calculate the flow rate of that component. For the stream here, 0.885 of it, that fraction of it is our water. So we take 0.885 multiplied by 400, that's an input. As we work our way around, there's no water in this other input stream. There is water in this output stream. The fraction of water in that stream is 0.995. The flow rate is m.r. So that's the amount of water that comes out as a product of those two. But there's also no water in the organic stream that comes out, so we don't add anything else to it. Our water balance only has those two streams, the one input stream and the one output stream. And if we write down the balance for the last component, C, which is the hexanol is only present in two streams, just like the water. It's in this one input stream, and the flow rate of it coming in is going to be 1, the mass fraction of hexanol times the flow rate m.c. That's the input stream. We're going to set that equal to what comes out, which is 0.904 times m.e. And so we've written all four balance equations that we can write for this particular control volume. Next, let's look at each of these equations and see if there's one of them that we can solve for one of the unknowns. We just work our way down the list. We're not going to be able to know where to start. We just have to start in looking at each one and work our way down until we find one that we can use. The first equation has 3 unknowns in it. We won't be able to solve for one of those from that equation. The overall balance we can't use. If we look at the balance for acetic acid, it has 2 unknowns. If we look at the balance for water, we find as this equation has only 1 unknown. So let's use this equation to solve for that 1 unknown, which is m dot sub r. If we rearrange that equation, m dot sub r is just going to be 0.885 times 400 divided by 0.995. That's 356. That's a great start. Next, let's plug in this value for m dot r into the other balances and see if there's one that we might be able to use to solve for another unknown. If I look at the overall balance, if I plug in a value for m dot r, I'm still left with 2 unknowns, m dot c and m dot e. If I look at the acetic acid balance, if I plug in for m dot r, I will only have 1 unknown left, m dot e. So I'll be able to solve for it. Let's do that. So I'll take the balance for equation for acetic acid, move it down here. On the left-hand side, we still have 0.115 times 400. On the right-hand side, we're going to have the 0.005 times m dot r, which we now know is 356. And that's going to be added to 0.096 times m dot e. This equation can be solved for m dot e. We'll take the quantity on the left, the 0.115 times 400, subtract from it the product of 0.005 times 356, and then that result will be divided by 0.096 to get m dot e, which turns out to be 460. Finally, now that we know m dot r and m dot e, let's see if we can solve for one of the other balance equations for m dot c. If we just start down our list, we start at the top up here with the overall balance. What we find is that if we know m dot r and m dot e, which we now do, we can solve this for m dot c. And so we'll take this equation down here, and we'll rewrite it as 400 plus m dot c. We still don't know m dot c is equal to m dot r, which we decided is 356. We'll add to it m dot e, which we have decided is 460. And we solve this equation for m dot c, we end up with m dot c is 416. So we solved for all the unknowns. We did it with using 3 of the 4 equations that we had written. We can check our calculations with the last balance equation that we hadn't used for doing any of the calculations. Let's just see if we find that this equation is satisfied. On the left-hand side, we plug in m dot c, which we determined was 416, and we ask ourselves, is that equal to 0.904 times the value we have calculated for m dot e? We take 0.904 multiplied by the value we calculated, which is 460. We find it is indeed equal to 416. So it looks like we did the calculations correctly. The last example we're going to work in this lecture is the one for which we labeled streams in the previous homework assignment. In this particular example, we're taking strawberries, which contain 15% by weight solids. We'll use the symbol S to denote solids. And the balance, the remaining 85% by weight, is water. We'll use the symbol W to represent it. Now to make berries, we're going to take some amount of, or to make jam, we're going to take some amount of the crushed berries, and then we're going to mix them with sugar, and we're going to use the symbol G to represent sugar. Now the berries and the sugar are mixed in a ratio of 45 to 55. So 45 grams of berries will be mixed with 55 grams of sugar. Or you could think of this as 45 kilograms of berries are mixed with 55 kilograms of sugar. And then this mixture is heated, and as it's heated, water will evaporate and be removed until the residue, what's left behind, contains 1/3 water by mass. And it's this residue which will hopefully be our tasty jam. Now we drew this process as part of the previous homework assignment, and we labeled each of the streams as you see here. I'm just going to go around this evaporator here, this process, and make sure that we are familiar with the symbols, and just to review the results that we got from the previous time. So the amount of berries that we're feeding to this evaporator is represented by the variable m sub 1. We weren't given an amount that we're adding here, but we're going to mix this amount, m sub 1, pounds mass of berries, with some unknown amount of sugar, m sub 2, pounds mass of sugar. And then once we heat it, we're going to evaporate some amount of water. The symbol m sub 3 will represent the mass of water that evaporates, and will be left behind then with a mass m sub 4 of jam. All of these masses are unknown. None were specified in the problem statement. Below the arrows for each stream are the composition data that we know. For the berries, we know it's 15% solids, so mass fraction of solids is 0.15. The balance is water. The sugar is pure sugar. There's no solids or water in it, so the mass fraction of sugar is 1. The water we evaporate is pure water. The mass fraction of water is 1. And then we look at the jam. We're told it's 33 point, or a third, by weight water, so the mass fraction of water is 0.333. We don't know the solids composition, so we'll represent it by the variable x sub 1. And then the fraction of sugar we can calculate by requiring the fraction of sugar when added to the fraction of water, when added to the fraction of solids, summed to 1. And that tells us that the fraction of sugar has to be 0.667 minus x sub 1. And we can check that by adding these together, adding x1 to 0.333, then adding that to 0.667 minus x1. And if you do that, you'll find you do get 1 when you sum these up. So let's determine the problem solvable. For this steady state process that has no chemical reactions, what that means is that the number of unknowns has to be equal to the number of equations that we can write, which is equal to the number of components. So let's count the number of unknowns. If we go our way around, we'll start up here on the upper left. M1 is an unknown. M2 is a second one. We work our way over here to the upper right. M3 is a third. M4 is a fourth as we come down to the jam. And X1 is the fifth. We have 5 unknowns. The number of equations independent equations, balance equations we can write is equal to the number of components. The number of components are 3. We have solids, water, and sugar. 5 is greater than 3. We have more unknowns than equations we can write. In order to solve for these unknowns, we have to have 2 additional pieces of information that we can translate into equations, so the number of equations we have is equal to the number of unknowns. Let's go back to the problem-solving process and look at step 4 again. If no flow rates or amounts are specified, we can choose a basis for the calculation. We can choose an amount for any one of the streams. Now, since none are given, let's just assume that we have 1 pound mass of berries we're going to be mixing. So we'll put 1 up here for m sub 1. We'll replace m sub 1 with the numerical value 1. Now, we could have replaced any of the other 3 amounts. This was an arbitrary choice. But you would end up getting the same results if you chose any of the others. Now, I'll show you how you can convert between the different ones at the end of this problem. So if we decide to set M1 equal to 1, take this as our basis for the calculations, that's how it's technically referred to, then the number of unknowns reduces from 5 to 4. We eliminated M1 from the list here. The number of components hasn't changed, so the number of independent equations is still 3. That means we need 1 additional piece of information. And this is where we need to go back and reread the problem statement and see if there's something there that, and we did talk about this, is that there was one additional statement there that the ratio of the mass of berries to the mass of sugar that we add to this evaporator to make jam is 45 to 55. So let's write this in terms of the masses that we have here on our process flow diagram. We chose as a basis 1 for the mass of berries. We don't know M2. We do know that that ratio, 1 over M2, is going to be equal to the ratio of 45 to 55. So we can solve for M2. M2 is just 55 over 45. It's 1.22. So we can add that number to our process flow diagram here. This was a key step. It's going back, rereading the problem, and making sure there wasn't some piece of information that we overlooked or thought might not be important, and see if that helps reduce the number of unknowns that we have. Now, the number of unknowns has reduced to 3, and the number of equations that we have are 3, so the problem's solvable. Let's proceed with trying to determine each of those values for each of those unknowns. For this batch process, everything we put in is taken out, and there's no reactions that occur. So accumulation is going to be equal to generation terms, is going to be equal to consumption terms, is going to be equal to 0. And we can say that what comes in is equal to what comes out. The control volume we're going to use is shown in red here, this red square. And the 4 balances that we can write are indicated here below. There have been summarized for you here. Now only 3 of these are independent, because this overall balance we can obtain by taking the solids balance, adding to it the water balance, and adding to that the sugar balance. So if I add up these 3 bottom ones, I'll end up with the overall one. The reason we write all 4 is that it may turn out that the overall balance is easier to solve than either of the other species balances. So I'm going to go through one of these and leave the rest for you to look at, or 2 of them, leave the rest for you to look at on your own. So let's look at the overall balance, and we're going to work our way around the control volume and determine where arrows cross the control volume, and where an arrow crosses will determine what term to add to our balance equation. So let's start up here in the upper left-hand corner of the control volume. There's one stream that enters here, and that's the fresh strawberries that we're adding. And we're adding 1 pound mass of it. So we'll put that 1 as on the input side of the equals over here in our overall mass balance equation. Let's work our way around clockwise. As we come around, we encounter the first output from the process, which is the water that's evaporated. Its amount, total amount, is given by the variable M3. So we'll add this to the right-hand side of the equals in our overall mass balance. That's one of the outputs from the process. We keep on going around the control volume. We encounter one more output, which is the jam, and the total amount of it is M4. We'll add M4 to M3 to determine the total amount that comes out. And if we keep on going around our control volume, we have one more input, which is the sugar, and its mass is 1.22. So we'll add the 1.22 to the 1 to get our total amount coming in. And since we've gone completely around the control volume, this now represents our overall balance. If we look at this, ideally this would be an equation that we could solve for one of the unknowns, and unfortunately there's 2 unknowns in this equation, M3 and M4. We can't solve for either one of them. So let's hope that one of the other balances, the balances that we've written for the solids, for the water, and for the sugar, hopefully one of those will be, we can solve for one of the unknowns from one of those equations. If not, we're going to have to resort to solving 2 equations and 2 unknowns, or even worse, 3 equations or more, and 3 or more unknowns. So let's do the solids balance, and then we're going to move on after that, and I'll let you verify that the water balance and sugar balances are correct. So the solids balance we're going to obtain in exactly the same way. We're going to start up here in the upper left-hand corner and determine the flow rate of solids coming in, each of the arrows that cross our control volume. So for this arrow here, we do have solids in it, so there will be a term that we'll have to add in. We know that there is the mass fraction of solids in this stream is 0.15, so I'll take this number, multiply by the total amount of that stream to get the amount of berries that's coming in. And that will be on the left-hand side of the equals here, one of the input terms for our solids balance, 0.15 times 1. And then we're going to start here and work our way around the control volume. We go over here to the water, evaporated water stream. There's no solids in it, so it won't contribute to the solids balance. If we keep on coming down, we find that there is solids in the jam that's coming out. The fraction of the total amount of jam that is solids is x1. So x1 times m4 will be equal to the amount of solids coming out in that stream. And I'll put that term on the right-hand side of the equals as an output. Now continue around our control volume. The next stream that we encounter is this one coming in, the sugar. There's no solids in it. It's pure sugar, so it won't contribute anything to our solids balance. As we come back, we've completed looking at all the streams that cross the control volume, and this now represents the final equation, the final balance for the solids. And if we look at this, can we solve for one of these unknowns? Well, unfortunately not. This equation has two unknowns in it as well, x1 as well as m4. Let's look at the other two balances, which I haven't gone over in detail how we got them. Let's look at the water balance and ask ourselves, is this one equation that we can solve for one of the unknowns? And unfortunately, no. This equation involves both M3 and M4. And the last equation, the sugar equation, the sugar balance, we look at it, it too has two unknowns in it, x1 and m4. So it looks like none of these equations can be solved directly for one of the unknowns. So what we have to do is solve two of the equations simultaneously. And to determine which two to solve requires a little bit of trial and error. If you look at the four equations on the previous slide, you'll see that the overall balance and water balance probably are the simplest set of equations to solve simultaneously. And those are just simply rewritten here on this slide. This is the overall balance in the previous slide, and this is the water balance. And we can solve these two equations as they are written by simply subtracting the water balance from the overall balance. We're going to do this term by term. What we're going to do is on the left-hand side, the sum of these two numbers is 2.22. And I'm going to subtract from it the term on the left-hand side from the water balance, which is 0.85. So I'll take this amount and subtract this, 2.22 minus 0.85, and then set that equal to what's on the right-hand side of the overall balance minus what's on the right-hand side of the water balance. If I do this, I'll take M3, subtract M3, that gives me 0. The M3 cancels out. If I look at the M4, I'll have M4 minus 0.333 M4. And after I've done then the subtraction of the water balance from the overall balance, I end up with this equation, which is an algebraic equation that we can solve for M4. And if you follow the steps here, you end up with M4 being equal to 2.05. Let's go back to these two equations here and see what made it possible to solve for one of the unknowns. What made it possible in doing the subtraction is the fact that we had a coefficient of 1 in front of M3 in the overall balance and a coefficient of 1 in front of M3 in the water balance. So we could subtract these two and have the M3 terms cancel out. If we didn't have that, what we could do is take one of the equations and multiply it by something that will convert the exponent of M3 in the overall balance to the same value in the water balance. Or if we had the M4 term, we can multiply it by a number that would convert the coefficient of M4 in this equation to the coefficient in the water balance. So for instance, if I had taken the overall balance and multiplied by 0.333 and then subtracted, this term here would cancel with this term, and we'd be left with an equation that involved M3 alone. Now I'm going to go through this in detail. I would ask that you play around with this and practice this on your own, how you combine two equations and two unknowns to solve them. What I've shown you here is one way to do it. I'm sure you've learned other ways to solve two equations and two unknowns. And in fact, you may have a calculator that would do that for you. Excel will do it for you as well. But this is one of the nuances of solving these problems, that often you'll have to use some algebra that you may not be practiced in order to solve the equations for the unknowns. So let's look at the overall balance. Now that we know M4 is 2.05, we can plug that into the overall balance and solve for M3. It's 0.17. And those numbers both are shown up here on the process flow diagram. Then if we look at the solids balance, once we know M4, we can solve that for X1. So we plug in 2.05 for M4. We take this equation and solve for X1. It turns out to be 0.073. One of the questions you might ask is, how many pounds of strawberries do I need per pound of jam? Now, one thing that we can do is that we can rescale all the flow rates or amounts in a process flow diagram by multiplying them by the same factor. This won't change any of the compositions. All that will change is the amounts or flow rates. Doing this represents scaling them in a certain way. And we can scale them by multiplying by the same factor and not change any of the calculations. Don't have to go back and redo any of the calculations. So for instance, if we want to produce what the results are for producing 1 pound mass of jam, we could divide all the total amounts, all the masses, by 2.05. So this gets converted to 1, and then each of the other numbers will be converted to the value needed to get 1 pound mass jam. And that's what's shown here. We'll divide all the amounts by 2.05 to obtain the results for pound mass jam. So we look at the jam. If we take the 2.05 pounds of jam divided by 2.05, we get 1 pound jam. And all the other values here are converted by dividing by the same amount, 2.05. And the numbers then are indicated in the process flow diagram here above. And what we find out then is that 0.488 pounds mass of berries are required for every pound mass of jam. That's roughly about what you do use when you make jams, is you use about half of it's going to be sugar.